For basically 30 years, there's been this tiny silver sticker on your laptop.
Oh, yeah. Right below the keyboard.
Exactly, down there on the bottom left. And it usually says Intel Inside.
A total classic.
Right. And it was basically a seal of approval. It meant your computer was a real computer, capable of doing real work.
Yeah, it meant you had serious hardware.
But today, that sticker and really the entire philosophy of personal computing that it represents is, well, it's becoming obsolete.
Completely obsolete.
Welcome to the deep dive. It's early June 2026, and the tech world has just been completely turned upside down at JTC Taipei. We're looking at a seismic shift here.
Yeah, it's not just a minor upgrade.
No, not at all. Because NVIDIA isn't just trying to put their name on your laptop. They're trying to turn your PC from, a reactive piece of glass and metal into an autonomous digital teammate, like something that actually thinks for itself.
It's a fundamental rewiring of what a personal computer is supposed to do, honestly. For the entire history of computing, the machine has been a passive tool. It waits for a keystroke. It waits for a mouse click.
It's sitting there.
Exactly. And then it executes a really highly specific command. But what NVIDIA unveiled at GTC Taipei with their new RTX Spark superchip is the hardware foundation for an active agentic machine.
Agentic, that's the big word here.
Right, a computer that anticipates, orchestrates, and executes complex multi-step workflows. And it does it entirely locally.
Okay, so let's unpack this. Because the sheer scale of what NVIDIA is claiming here is massive. We are building this deep dive on a stack of technical breakdowns from a source called Netizen PC, NVIDIA Inside, dated June 2, 2026.
Awesome source.
Yeah, really dense stuff. But the mission here is to understand NVIDIA's aggressive invasion into the heart of the Windows PC ecosystem. They're calling this new category AI-rich PCs.
AI-rich. I love that term.
Right. And just to set the baseline for you listening, we are not talking about the usual year-over-year tech bump. We aren't talking about a laptop that, renders a spreadsheet 10% faster.
Or gives you an extra 45 minutes of battery.
Exactly. That's the old paradigm.
Far from it. An AI-rich PC represents a total architectural teardown. To run massive frontier-level artificial intelligence models directly on a laptop, the traditional way we build computers, like the legacy by 86 architecture that's dominated since the 80s, it just hits a brick wall.
It just can't handle it.
Right. The bottleneck isn't just processor speed either. It's how the different parts of the computer talk to each other.
Yeah.
NVIDIA recognized that to make a computer think like an AI, you have to build the physical silicon differently.
So NVIDIA has built this massive new engine, right? The RTX Spark. And to really understand the software magic that is supposedly going to change our daily work lives, we first have to crack open the laptop chassis.
Get into the hardware.
Yeah, we have to look at the physics of what is actually happening on the motherboard. And the biggest shift here is NVIDIA moving away from discrete GPUs.
Which is a huge deal for them.
It really is. Because for a long time, if you bought a high-end laptop or a workstation, you had a central processing unit, the CPU, and then a totally separate graphics processing unit, the GPU.
Yeah, the discrete GPU was a completely separate physical card plugged into the motherboard. It had its own cooling, its own power delivery.
Right.
And crucially, it had its own pool of memory. So if the CPU was the management of a company, the GPU was like a highly specialized factory.
But they lived in different zip codes.
Exactly. They are fundamentally separated.
And if management wanted the factory to do something, they had to put the blueprints on a truck and literally drive it across town.
Yep.
In computer terms, that truck is the PCIe bus, right? The physical wiring connecting the CPU to the GPU.
That's a perfect visualization, honestly. And driving that truck back and forth takes time. And it burns an immense amount of power.
Right, which drains your battery.
Exactly. Now, in traditional computing, like if you're rendering a video game, that delay is manageable. The CPU tells the GPU where the character is, and the GPU draws the lighting and shadows.
It's a fairly linear process.
Right. But artificial intelligence, specifically the large language models we are dealing with today, they operate completely differently. These models are just staggeringly memory hungry.
So what happens with the truck then?
Well, if an AI is trying to process a complex request, It has to constantly shift gigabytes of data back and forth between the CPU's memory and the GPU's memory.
Over and over again.
Over and over. So that truck is constantly driving back and forth, creating this massive traffic jam. It drains the battery, it generates a huge amount of heat, and it slows the AI inference down to a crawl.
Okay, so this is where NVIDIA's shift to an Antor, a system on chip, totally changes the physics of the board. The RTX Spark isn't a separate card anymore.
No, not at all.
It puts the CPU and the GPU on the exact same piece of silicon. They are, to use your analogy, they're in the same high-rise building now.
Which eliminates the commute entirely.
Exactly. But the real key here, and the thing that blew my mind in the source material, is what they are doing with the memory. They aren't just giving the CPU and GPU their own separate RAM banks on the same chip.
Right, they're using what they call unified memory.
Unified memory, and the numbers here are just staggering, up to 128 gigabytes of unified memory on a consumer machine.
I know, it's wild. But that unified memory is the absolute silver bullet for local AI.
Why is it so critical?
Well, instead of having separate filing cabinets for management and the factory, there is just one massive central filing system that both processors can access instantaneously.
Okay.
So when you load a massive AI model into a machine with 128 gigabytes of unified memory, the model just sits there. It doesn't have to be copied back and forth over a slow bus.
The truck doesn't have to drive anywhere.
Exactly. The GPU's thousands of CDA cores can reach directly into that memory and perform the complex matrix math required for AI inference with, like, zero friction.
Okay, so let's look at the actual processors that are sharing this memory. Because NVIDIA isn't doing this entirely alone, right?
No, they brought in some heavy hitters.
Yeah, the CPU side of the RTX Spark is actually ARM-based. The source says they built it in partnership with MediaTek, drawing on NVIDIA's own enterprise-grade Grace architecture.
Yeah, Grace is serious stuff.
Right, and then they paired that with a GPU built on their Blackwell architecture. And just for context, Blackwell is the same fundamental architecture powering those massive server racks in data centers right now.
Which is insane to think about in a laptop. Because by combining the ARM-based CPU with the Blackwell GPU, NVIDIA achieves this level of computing density that was previously just impossible in a portable form factor.
Density is a good word for it.
Yeah, and that density translates directly into raw output. I mean, the RTX Spark is rated to push roughly 1 petaflop of AI performance.
Okay, 1 petaflop. Let's pause there. That's 1 quadrillion operations per second.
Yep.
A decade ago, a petaflop required a literal warehouse full of supercomputers, right? Complete with industrial liquid cooling systems and, like, a dedicated power substation.
You practically needed your own dam to power it.
Exactly. And now NVIDIA is claiming it fits in a backpack. But wait, I have to push back on this number a little bit.
I'll go for it.
Because the technical breakdown from our sources specifies that this is 1 petaflop of AI performance specifically in FP4 precision.
Right, FP4.
It feels like there's a big asterisk on that petaflop. Like if I'm rendering a 3D scientific simulation of, I don't know, fluid dynamics, I need incredibly precise math. I need floating point 32 or FP32.
Right, absolutely.
So if NVIDIA is touting this massive number, but it only applies to this lower FP4 precision, isn't that just a marketing trick?
I totally get why you'd say that. It sounds like an asterisk until you look at the mechanics of how a neural network actually thinks.
Okay, break that down for me.
So you mentioned fluid dynamics. If you are calculating the exact stress on an airplane wing at supersonic speeds, yes, you absolutely need FP32.
Because if you're wrong, the wing falls off.
Exactly. You need decimal places stretching out into infinity because a rounding error is catastrophic. That is highly deterministic, precise math.
Right.
But artificial intelligence inference, how these models process data, is probabilistic. It is essentially just pattern recognition and prediction.
Probabilistic. So it's guessing.
Kind of, yeah. Like, if the AI is looking at a picture and trying to determine if it's a cat or a dog, it doesn't need to calculate the exact molecular structure of the fur to 32 decimal places.
No, it just needs to know it's fluffy and has pointy ears.
Precisely. To recognize the pattern of cat, the neural connections just need a general weight. Like, is this connection strong, weak, or somewhere in between?
I'm piping.
So FP4, which is 4-bit floating point precision, only provides a very limited number of values. It's like, think of it like turning a high-resolution, full-color photograph into a slightly pixelated, limited-color image.
Oh, that's a great way to think about it.
Right. The really fine details are gone, but you can still immediately tell it's a picture of a cat.
Yeah.
For generating text, summarizing documents, or like controlling user interfaces. An AI model quantized down to FP4 precision loses almost zero functional accuracy.
Wow, really? Almost zero.
Almost zero. But here's the magic. It drastically shrinks the size of the model.
Okay, so by shrinking the mathematical precision needed to guess the next word or identify a pattern, the data takes up vastly less physical space in that 128 gigabyte unified memory.
You got it.
And because it's smaller, the Blackwell GPU can chew through those calculations vastly faster.
Exactly. That's how they hit 1 quadrillion operations per second on a laptop. They are doing simpler math, but they are doing it with unbelievable speed and efficiency.
And that efficiency is basically the entire ballgame here. You don't need a warehouse power substation because FP4 math on a Blackwell core, directed by a highly efficient ARM CPU, it just sips electricity.
It's incredibly elegant engineering.
But, I'm still a little skeptical about the physics of this in the real world. Let's ground this for a second. We've had incredibly powerful gaming laptops for years, right?
Well, yeah, huge, heavy things.
Yeah. They have top-tier CPUs, massive discrete graphics cards, and tons of RAM. And they are absolutely miserable to use away from a desk.
Clue.
Like the battery dies in 45 minutes. And if you open a heavy 3D application, the fans kick on and sound like a jet turbine.
And the keyboard gets so hot you could literally fry an egg on it.
Exactly. So is slapping a powerful GPU and CPU together onto one chip really solving that heat problem?
Well, the heat problem in those traditional gaming laptops stems from two things. First, the x86 CPU architecture itself, which is just incredibly power hungry.
Right.
And second, the physical separation of the components, which we talked about. Because they are separate, you have to brute force electricity across the motherboard just to move the data.
Over the PCIe bus.
Right. But because the RTX Spark uses an ARM-based CPU,
Yeah.
which is, by the way, the exact same fundamental low-power architecture that runs your smartphone, it generates a fraction of the heat.
Because my phone doesn't have a fan.
Exactly. And then the unified memory means data isn't being shoved back and forth across the board. You are completely eliminating that physical friction.
And so the promise here is not just raw power. It is sustained, quiet power.
Exactly. Slim laptops with all-day battery life that can simultaneously run AI models that would have completely melted a gaming laptop just 3 years ago.
Okay, so the hardware is clearly a marvel of efficiency and density. But NVIDIA isn't just a hardware company, are they?
Oh, not at all. They're a massive software ecosystem.
Right. And this superchip works because NVIDIA is bringing their entire enterprise software stack down to the consumer level. The sources mentions CUDA, TensorRT, the RTX feature sets.
Which is huge for developers.
Yeah, like if you are an AI developer today, you are probably already building your tools using CUDA. It's basically the lingua franca of AI development.
It absolutely is.
So by ensuring the RTX Spark runs CUDA natively, NVIDIA guarantees that on day one, every major AI application out there will run flawlessly on this new hardware.
Which fundamentally changes where artificial intelligence lives. The unified memory, the FP4 petaflop performance, the CUDA integration, it all serves one single really profound goal.
Which is?
Cutting the cord from the cloud. We are witnessing the dawn of mainstream edge AI.
Okay, let's explore that. Because for the last few years, the AI revolution has been entirely dependent on massive data centers.
Yeah, the cloud AI model.
Right. Like when I open a browser and type a complex prompt into a large language model, asking it to, say, write a Python script or summarize a massive legal brief, my laptop isn't actually doing any of the thinking.
No, it's basically just a dumb terminal at that point.
Right. It just sends my text over the internet to a massive server farm somewhere in Virginia or Oregon, those giant hyperscaler servers do all the heavy lifting, and then they beam the answer back to my screen.
And look, the cloud AI model was necessary to introduce the world to these tools. Because until now, no personal device had the actual physical capability to run them.
Sure.
But the cloud has massive structural limitations.
Like what?
Well, first is latency. Even with a fiber optic connection, there is a physical speed limit to sending data thousands of miles away, processing it, and sending it back.
Right. You always feel that slight pause. It isn't truly instantaneous.
Exactly. And second, it completely falls apart the second you lose your connection.
Oh, tell me about it. I remember trying to use an early cloud-based AI feature to draft an email on a train once.
Let me guess, you went through a tunnel.
Yep. We went through a tunnel, the connection dropped to 3G, and the entire application just froze. I got the spinning wheel of death.
Yeah, that's the reality of cloud dependence. Beyond reliability, though, there is the sheer cost.
The cost to the companies running it.
Yeah. Every single time a user asks a cloud AI a question, it costs the provider money and server electricity and compute time. This is exactly why API limits exist.
Oh, so that's why you get throttled if you use a tool too much.
Exactly. But the most critical limitation of cloud AI, and this is the absolute deal breaker for wide-scale enterprise adoption, is privacy.
Privacy. Okay, yeah, that makes total sense. If you are, say, a doctor analyzing patient medical histories, or a defense contractor reviewing engineering schematics,
Or a corporate lawyer reading unreleased financial data.
right, you absolutely cannot send that information to a server farm in another state.
It is a massive compliance violation.
Yeah.
You don't know who actually owns that server. You don't know if your proprietary data is being ingested to train their next model, and you are exposing yourself to interception over the open web.
Yeah, that's a non-starter. So the shift to edge AI solves every single one of those problems, doesn't it?
It does. And the edge simply refers to the outer boundary of the network, so your actual physical device.
Your laptop.
Exactly, your laptop. The RTX Spark allows the local execution of what the industry calls frontier-level models.
Okay, the breakdown defines frontier-level models as having tens to low hundreds of billions of parameters.
That's massive.
It is. Let's do the math on what that actually means for the hardware, because this ties right back into the 128 gigabytes of unified memory we discussed earlier.
Let's do it.
So a parameter is essentially a single connection in the AI's neural network, right?
Roughly speaking, yes.
Okay, so if we take a model with 100 billion parameters and we quantize it down to that highly efficient FT4 precision we talked about.
Which is 4 bits per parameter.
Right, 4 bits or half a byte. That model requires roughly 50 gigabytes of memory just to sit idle.
Your math is spot on. And in the old world, trying to load a 50-gigabyte model into a discrete GPU was literally impossible.
Because the cards didn't have that much memory.
Right. The VRAM simply didn't exist on consumer cards. Most cards had maybe 16 or 24 gigs. But with 128 gigabytes of unified memory, that massive 100 billion parameter model just slides right in.
Taking up less than half the available space?
Exactly, leaving plenty of room for the operating system and all your other applications.
So you essentially have the smartest consultant in the world sitting right there on your hard drive.
And because it is local, the privacy issue just totally vanishes. The AI model comes to your data, not the other way around.
I think that's a huge distinction.
It is. A doctor can feed thousands of pages of highly sensitive patient records into the local AI to look for patterns or cross-reference drug interactions, and not a single byte of that data ever leaves the physical chassis of the laptop.
You could literally turn the Wi-Fi completely off.
Exactly. The sovereignty of your data is guaranteed. And going back to the latency issue, there is no latency. It responds as fast as you can type.
But here's where it gets really interesting and where I think a lot of people struggle to see the vision of why this matters for the average person.
How so?
Well, if these local models have hundreds of billions of parameters, how does that actually change my Tuesday morning? I mean, isn't the cloud fast enough for writing an email or, rewriting a sentence to sound more professional?
Right. Do we really need a supercomputer for that?
Exactly. Do we really need a localized AI supercomputer just to fix our grammar?
Well, if the end goal of AI was simply grammar correction, then yeah, the cloud would be perfectly sufficient. But what Edge AI enables is deep, persistent, system-wide integration.
What does that look like in practice?
A cloud AI only knows what you explicitly paste into its chat box. It has absolutely no context for who you are or what you do.
Right, it's a blank slate every time you open it.
But a local AI running constantly in the background on an RTX Spark has secure access to your entire digital life.
Oh, wow.
Yeah. It can index every single PDF on your hard drive. It can read your local email archives to understand your specific communication style. It can monitor your calendar to understand your schedule.
Okay, so it's the difference between hiring a consultant who you have to brief on every single detail before they can answer a question versus like an assistant who has been sitting in your office for 5 years and already knows where all the files are buried.
That is the perfect analogy. And importantly, this doesn't mean the cloud just disappears. The architecture of the future is hybrid.
Hybrid, meaning both.
Yes. The cloud still has a massive role to play in the training of these models. If you are building a new model from scratch, feeding it trillions of tokens of text to teach it a new language or a new scientific discipline, you absolutely still need a warehouse of servers.
So the cloud is the university where the AI goes to get its degree.
I love that. Yes.
But the edge, meaning your PC, is the office where the AI actually does its daily job.
That is a brilliant way to frame it. The heavy lifting of training stays centralized, but the personal real-time inference moves locally to the user.
Okay, but NVIDIA's hardware is just metal and silicon, right? I mean, it creates the environment. The
Yeah.
local processing ensures the privacy and the speed. But a V8 engine is useless if the car's steering wheel isn't connected to the tires.
Very true.
For this to actually work, for this local AI to seamlessly interact with your files and your calendar, the operating system has to know how to drive the hardware.
And that's where the software gets really exciting.
Which leads us into the software layer and NVIDIA's crucial alliance with Microsoft. How is Windows changing to actually talk to this new silicon?
Well, this partnership is really the linchpin of the entire AI-rich PC strategy. NVIDIA provides the muscle, but Microsoft provides the nervous system. They are collaborating incredibly deeply to make Windows natively aware of the RTX Spark.
Because Windows historically hasn't worked like this.
No, the old way of building Windows was essentially creating a passive grid. You have a desktop, you have folders, and you launch executables. The user provides all the momentum.
Right. If I want to send a file to a colleague, I have to find the file, open my email client, create a new message, attach the file, and hit send. I am doing all the driving.
Exactly. But Microsoft is shifting Windows to what they call an agentic platform.
There's that word again. Agentic.
Yep. They are integrating NVIDIA's OpenShell technology with their own deep OS enhancements. What this means is that Copilot, which is Microsoft's AI assistant, is moving from being a chatbot that just lives in a sidebar to becoming an autonomous agent that is deeply embedded in the kernel of the operating system.
Wait, so an agentic platform means the AI doesn't just suggest things. It actually takes action. It can control the UI.
Yes, it operates across the application layers.
So it's actually clicking things for me.
Basically, instead of you clicking through 5 different programs, you give the Copilot agent a high-level goal. You say, send the Q3 financial report to Sarah and summarize the key revenue changes in the email body.
And it just does it.
The agent understands the context, locates the local Excel file, reads it using the local AI model, drafts the summary, opens Outlook, and prepares the email.
That is wild. And for Microsoft, this represents a massive strategic victory in what the industry calls the AI experience war.
Oh, totally. A huge win.
Because over the last few years, Microsoft has pushed Copilot incredibly hard, but it was heavily reliant on those expensive latency-prone cloud APIs we talked about. They were paying the server costs every time someone asked a question.
Millions of dollars in server costs.
Right. So by shifting Copilot to run locally on NVIDIA's hardware, Microsoft dramatically reduces their server overhead.
It reduces their costs, absolutely. But more importantly, it creates this impenetrable moat around the Windows ecosystem.
What do you mean by moat?
Well, if Windows becomes the only platform where your AI teammate can seamlessly interact with all your local files and applications with zero latency and total privacy, the switching costs for a consumer or an enterprise become impossibly high.
Because you'd have to leave your assistant behind.
Exactly. You are locked into the platform because the platform is literally where your intelligence lives.
Wow. And Microsoft and NVIDIA aren't just targeting the everyday office worker with this alliance either. They are making a massive play for developers.
Huge play.
The technical breakdown explicitly mentions full CUDA support on Windows, specifically routed through WSL, the Windows subsystem for Linux. Break down how WSL actually functions, because this is a pretty massive shift in how AI development has traditionally worked.
Yeah, so historically, if you were a serious AI researcher or developer, you did not use Windows.
Right.
Artificial intelligence development is almost entirely built on Linux. The tools, the libraries, the frameworks, they all natively expect a Linux environment.
So developers either had to use a dedicated Linux machine or they rented really expensive Linux server space in the cloud.
Exactly. But the Windows subsystem for Linux, or WSL, allows a developer to run a genuine Linux kernel inside Windows. It uses a lightweight virtual machine.
But usually when you run a virtual machine, there is a massive performance tax, right?
Usually, yeah.
Because the virtual machine has to translate all its commands through the host operating system before it can even talk to the hardware. It's like trying to run a marathon underwater.
That performance tax was the historic roadblock for doing this kind of heavy work in WSL. But the engineering miracle NVIDIA and Microsoft achieved here is called GPU pass-through.
GPU pass-through.
Right. They completely rewired the architecture so that the Linux environment running inside WSL can bypass the Windows kernel entirely. It talks directly, natively to the Blackwell GPU and that 128 gigabytes of unified memory.
Oh, wow. So the developer gets the sleek, user-friendly Windows interface for their daily life, Netflix, Office, web browsing. But when they open their terminal, the AI tools think they are running on a bare metal Linux supercomputer.
Exactly. There's no performance penalty.
Literally zero penalty.
Zero penalty. The sources call this the desk-side AI supercomputer, and it completely democratizes AI development.
How so?
Well, think about a computer science student in their dorm room, or a small startup working at a garage. They no longer need to secure venture capital just to pay for cloud computing time to train their models.
They can just do it on their laptop.
They can fine-tune frontier-level models locally. They can experiment, break things, and iterate at the speed of thought entirely for free on the exact same machine they use to write their term papers.
It's an incredible technical achievement. But I have to stop and ask the obvious question here.
Oh, I know where this is going.
Right. If the operating system is suddenly an agentic platform, if it has the power to control the UI, open applications, read my local files, and execute multi-step workflows autonomously, how do we prevent this from becoming an absolute nightmare? What happens when a localized agent goes rogue or, just misunderstands a prompt and accidentally deletes a critical project directory or emails a highly confidential draft to my entire contact list?
That is the defining tension of this new era, without a doubt. The transition from a reactive tool to a proactive agent introduces immense risk.
It has to.
And the foundational documents are acutely aware of this. They highlight the absolute necessity of ensuring agents are reliable and controllable. Security isn't just an afterthought here. It has to be the bedrock of OpenShell and the Windows integration.
But how do they actually enforce that? Because if the AI has kernel-level access to do its job, doesn't it have kernel-level access to destroy my life?
Well, they enforce it through strict, granular delegation of authority. The agents operate within highly constrained sandboxes.
Okay, sandboxes.
Yeah. They use a permission model that's kind of similar to how smartphone apps work today, but infinitely more complex.
So it asks for permission to do things.
Exactly. The AI might have read access to your files to analyze data, but it requires cryptographic, explicit user confirmation before it has write access to delete or modify a file.
Right.
Or before it can establish an outbound network connection to send an email.
Okay, so it's like having a very eager, highly intelligent intern.
That's a good way to look at it.
You trust them to read the brief, you trust them to draft the response, and you even let them format the email. But you absolutely do not give them the password to hit the send button without you reviewing it first.
Exactly. The human in the loop remains the ultimate failsafe.
And that human-in-the-loop dynamic is exactly what leads to the productivity revolution we need to talk about. We've established the hardware efficiency, the edge privacy, and the agentic OS integration.
Right.
But how does this actually manifest in a professional environment? The sources draw a pretty fascinating historical parallel here. They compare this transition to the shift between pre-web PCs and post-web PCs.
It's a really strong comparison.
I mean, I remember the pre-web PC era. In the early 90s, a computer was basically a digital typewriter and a calculator.
Yeah, maybe solitaire if you were lucky.
Exactly. You had your word processor, your spreadsheet, maybe a few localized games. It was an incredibly useful tool, but it was an island. It was completely isolated from the rest of the world.
But the arrival of the World Wide Web didn't just add a new application to the computer. It fundamentally changed the nature of the device itself.
The isolated island became a dynamic node.
Right, a globally connected node for commerce, research, communication. The document argues that the arrival of on-device AI is a parallel leap.
We are moving from the pre-AI PC to the post-AI PC.
Yes, the machine is evolving from a reactive workstation into an entire digital office.
Let's make this tangible for the listener. We used to think of a computer as a very fancy hammer. It was a tool that amplified human physical input. If you stopped swinging the hammer, if you took your hands off the keyboard, the construction stopped.
The computer just sat there idle.
But with an AI-rich PC, the computer becomes the entire construction crew.
And you are no longer swinging the hammer.
I'm just telling them what to build.
You are the architect. You are standing in the center of the site, holding the blueprints, pointing at what needs to be built, and coordinating the team. One of the most powerful examples of this in the text is voice-driven creation. And we need to be clear here. This isn't the basic, frustrating voice dictation we've had for a decade. where you slowly enunciate words and it still gets them wrong.
Oh, I hate that stuff. Period. New paragraph.
Right, this is not that. This is natural language orchestration.
Okay, so what's an example?
Well, the sources point to massive creative workloads. Imagine you are a video editor. You have an RTX Spark machine with 128 gigs of unified memory. You can speak naturally to your computer, pull the raw 12K footage from yesterday's shoot, find all the clips where the subject is smiling, color grade them to match a cinematic warm tone, and assemble a rough cut on the timeline.
In a traditional workflow, editing 12K video requires proxying the footage down to a lower resolution just to scrub through the timeline without the computer completely crashing.
It's a huge pain. You spend hours manually tagging clips and applying color masks frame by frame.
But with this,
But with a localized AI agent, utilizing the Blackwell tensor cores directly on that unified memory, the AI is buffering the full resolution footage, analyzing the visual data for facial expressions, and applying complex color transformations in real time.
it is happening locally in minutes.
Any minutes.
And it isn't just one agent working sequentially either. The document outlines the concept of concurrent agents. This is where the kitchen analogy really helps visualize the workflow.
Oh yeah. How does the kitchen analogy work in this context?
Well, think of a high-end restaurant kitchen. If you are a traditional PC user, you are a solo chef. You have to chop the onions, then you walk over and stir the soup, then you run to the oven to check the roast, and then you try to plate the appetizer.
Right, you're doing everything yourself.
You can only do one thing at a time, and you are constantly bottlenecked by your own physical speed.
A highly stressful and inefficient way to cook.
Exactly. Concurrent agents turn you into the executive chef. You are standing at the pass, overseeing everything. You have an AI sous chef aggressively chopping the data for a financial report. You have a pastry chef in the corner rendering that massive 12K video timeline. You have a sommelier at the front managing your incoming emails and sorting your schedule.
And they are all working simultaneously.
Yes, sharing the exact same pantry, that 128 gigabytes of unified memory, without bumping into each other or slowing each other down. And you are just tasting, adjusting, and directing.
And that level of concurrent execution is exactly why the sources claim the gap between an AI-rich PC and a traditional PC will feel as stark as the gap between a dial-up modem and a gigabit fiber connection.
It's that big of a leap.
It really is.
Yes.
A single professional, armed with a team of concurrent agents, can now output the volume of work that previously required an entire department of junior employees.
But this brings us to a really uncomfortable existential question, doesn't it?
Yeah, I think we both know what that is.
If my laptop can source the video clips, apply the transitions, render the 3D scenes, write the boilerplate Python code, and analyze the massive data sets locally in seconds, what exactly is the human doing?
It's the big question.
Are we just enthusiastically designing the tools of our own obsolescence?
It is the most critical question facing the modern workforce. The optimistic view, which, to be fair, the industry heavily leans into, is that this doesn't replace the human, it elevates them.
Elevates them how?
It forces a transition from being a doer of manual digital labor to being a director of outcomes. Like if you are a graphic designer, your value is no longer your ability to quickly operate the pen tool in Photoshop to cut out a background.
Because the AI does that instantly.
Exactly. Your value is your aesthetic judgment, your understanding of the client's brand, and your creative vision.
It removes the friction of the medium. The human raises the ceiling of what is possible because they are no longer bogged down in the minutiae of the execution. I am the architect, not the hammer.
That's the hope, yes.
Okay, so we have this vision of a radically empowered workforce armed with local agentic supercomputers. When does this actually hit reality? Because all of this sounds like science fiction.
It sounds like 10 years away.
Right, but the documents say the shockwave hits this fall in 2026. This is happening right now. And it is going to cause an absolute earthquake in the hardware industry.
It is a profound disruption to the established world order of personal computing. The original equipment manufacturers, the OEMs who actually build and sell the laptops, are completely bought in.
Who are we talking about here?
Well, NVIDIA has lined up an aggressive initial wave for fall 2026. The launch partners are a who's who of the industry. We are talking about Asus, Dell, HP, Lenovo, MSI, and critically Microsoft Surface.
And they are immediately followed by a second wave from Acer and Gigabyte, right?
Yep. If you walk into an electronics store this fall, the entire premium aisle is going to be dominated by the NVIDIA Inside badge.
But the inclusion of Microsoft Surface in that initial wave, That is the clear signal of how deep the integration goes, isn't it?
Oh, absolutely. Microsoft builds the Surface hardware specifically to showcase the absolute best capabilities of the Windows operating system.
It's their flagship.
Right. By choosing NVIDIA's RTX Spark for their flagship devices, Microsoft is basically endorsing this ARM-based SoC architecture as the definitive future of the platform.
Which puts NVIDIA squarely in the crosshairs of the old kings of the hill.
Intel and AMD.
Exactly. For 40 years, the personal computer has been synonymous with the x86 processor architecture, dominated entirely by Intel and AMD. They own the PC market. And now NVIDIA is walking in with an ARM-based processor and trying to take the crown.
It's a huge threat. The x86 architecture is a complex instruction set computer, or CISC. It was designed decades ago to handle a massive variety of complex tasks directly in the hardware.
It's versatile.
It is incredibly versatile, but it is notoriously power-hungry and generates a lot of heat. ARM, on the other hand, is a reduced instruction set computer, or RISC.
Right, which means what?
It relies on simpler, smaller instructions that execute incredibly fast and use vastly less power. This is exactly why every smartphone on Earth uses ARM chips.
And we have seen this exact architectural war play out recently, haven't we?
With Apple.
Yes. A few years ago, Apple looked at the thermal limitations of Intel's x86 chips in their MacBooks. They realized they couldn't build the thin, silent, powerful laptops they wanted.
So they just ditched Intel.
They completely ditched them. They transitioned their entire lineup to their own ARM-based Apple Silicon, the M-series chips, and revolutionized their hardware. Battery life doubled overnight, and the fans basically disappeared.
Right.
NVIDIA is trying to orchestrate that exact same ARM revolution, but for the vastly larger, infinitely more complex Windows ecosystem.
But this is where NVIDIA faces their most dangerous hurdle.
What's that?
The risk of ecosystem fragmentation. See, Apple controls their entire stack, hardware, the OS, and the developer tools. When Apple transitioned to ARM, they could basically force developers to rewrite their apps.
Right, they have that control.
And they built a brilliant translation layer called Rosetta 2 that seamlessly converted old x86 code to run on the new ARM chips. Microsoft and NVIDIA do not have that absolute dictatorial control over the PC market.
Right. The problem is app compatibility.
A huge problem.
There are millions of legacy Windows applications out there, bespoke accounting software from 2012, specialized manufacturing tools, obscure indie games that were compiled specifically for x86 processors.
You physically do not know how to talk to an ARM processor.
Exactly. So if a consumer buys a brand new, premium AI-rich PC, opens it up, and their critical daily software crashes,
Yeah.
the revolution dies on the vine.
It really does. Historically, Microsoft's attempts to bring Windows to ARM chips, like the old Windows RT days, were absolute disasters precisely because of this compatibility failure.
Oh man, Windows RT? Yeah.
The emulation layers were terribly slow and apps constantly broke.
Now, the reports indicate that Microsoft has spent years rebuilding their emulation layer, currently called Prism, to be vastly more efficient. And major developers like Adobe and Google are already compiling native ARM versions of their apps.
Which is promising.
It is, but it is still a high-wire act. If the translation layer isn't perfect, the transition stumbles. And there is another massive hurdle in the data: the physical cost of building these machines in the current economic climate.
You are referring to the 2026 memory pricing cycle.
Right.
The tech industry projects explosive compound annual growth rates for these AI PCs. We're talking ranging from the high teens to over 40%.
Massive growth.
But the supply chain reality is that memory RAM is a highly cyclical commodity. Prices constantly boom and bust based on global fab production. And 2026 is currently experiencing significant pricing headwinds. Memory is just expensive right now.
Which creates a massive bill of materials problem for these laptops. We spent this entire deep dive establishing that the magic of the RTX Spark relies on that massive pool of unified memory.
That 128 gigs.
You need up to 128 gigabytes to run these frontier-level models locally. If a single 16-gigabyte RAM module is expensive right now, packing 128 gigs into a laptop is going to drive the manufacturing cost into the stratosphere.
It absolutely will. The bill of materials for these early AI-rich PCs is going to be significantly higher than a standard x86 laptop.
So if I am a consumer, aren't these machines going to be astronomically expensive? If an RTX Spark laptop costs $4,000, is this actually democratization of AI, or is it just a shiny new status symbol for ultra-rich YouTubers and C-suite executives?
In the immediate short term, fall 2026, you will absolutely carry a premium price tag. There's no getting around that.
Okay.
The initial target market is not the casual web browser. It is the creative professional, the developer, and the enterprise power user. But for those users, the high initial cost is easily justified by the productivity multiplier we discussed.
Because they aren't buying a computer, they are buying a localized private team of concurrent agents.
Ex-
If a $4,000 laptop allows a freelance video editor to take on twice as many clients because the machine is rendering effects and sorting footage autonomously in the background, that laptop pays for itself in the first month.
It is a capital expenditure that generates immediate return on investment.
Great.
Precisely. And the democratization happens over time. This is how all foundational technology works. NVIDIA is not treating the RTX Spark as a one-off experiment.
No, they have a plan.
The documents outline a multi-year aggressive roadmap. They already have the next architectures lined up, codenamed Vera Rubin and Rosa Feynman Spark.
Cool names.
Very cool. And as the manufacturing yields improve, as memory prices cycle back down, and as the architecture matures, the capabilities of today's $4,000 flagship will be the baseline standard in an $800 student laptop 3 years from now.
And when that trickle-down happens, the entire computing landscape is permanently altered. The pressure this puts on Intel and AMD is basically existential at this point.
It really is.
They have to accelerate their own internal AI hardware integrations, their NPUs, their localized memory architectures, or they risk being relegated to the history books, viewed as the purveyors of reactive, pre-AI legacy hardware.
If NVIDIA executes this transition successfully and navigates the ARM compatibility hurdles, they fundamentally diversify their massive empire.
Right, because right now, NVIDIA is the undisputed king of the cloud data center.
Exactly. But with RTX Spark, they capture the edge. They conquer the consumer desk. The personal computer essentially becomes a distributed node of a global AI factory.
It is a staggering amount of technical and strategic maneuvering to wrap our heads around. Let's pull the lens back and synthesize exactly what we've discovered today.
Let's do it.
We started by diving into the physical physics of the motherboard, exploring how NVIDIA's RTX Spark abandons the old discrete GPU model. By combining a hyper-efficient ARM-based CPU with a Blackwell GPU and pooling them around a massive 128-gigabyte unified memory architecture, they eliminated the traditional data bottlenecks.
We examined how that unified memory, combined with the computational trick of FP4 precision, allows these machines to push a petaflop of performance.
That crazy number.
Right. This hardware density makes mainstream edge AI a reality, pulling massive 100 billion parameter models down from the hyperscale cloud and running them locally. This guarantees absolute zero latency execution, totally offline reliability, and an unbreakable seal of data privacy.
And from the hardware, we moved to the software layer, unpacking the critical alliance with Microsoft. We saw how Windows is evolving from a passive grid of icons into an active, agentic platform where Copilot isn't just a chatbot, but an embedded kernel-level teammate capable of securely driving the UI and manipulating local files.
And we saw how tools like WSL with direct GPU pass-through turn a consumer laptop into a developer's dream.
We grounded all of this in the reality of the daily workflow, too. The transition from the solo worker swinging a digital hammer to the orchestrator managing a team of concurrent, specialized AI agents.
A paradigm shift that multiplies human output, allowing local machines to effortlessly handle 12K video rendering and complex data analysis simultaneously.
Finally, we surveyed the impending battlefield of fall 2026. The major OEMs rallying behind the NVIDIA Inside banner, the massive threat to the legacy by 86 architecture, and the very real hurdles of ARM emulation and the current memory pricing cycle that will define the early cost of adoption.
It is the most comprehensive reimagining of personal computing in decades.
It really is. And for you, listening to this, the implications are deeply personal. The tools you use every single day are about to radically change. You are standing on the precipice of upgrading from a digital typewriter to a highly capable digital entourage.
The processing power that used to require a corporate data center is going to be sitting quietly in your backpack, running on a battery.
That new sticker on the palm rest won't just mean your spreadsheets open faster. It means the machine you type on has the capacity to think, reason, and act alongside you, which leaves me with one final provocative thought.
What's that?
It's something that wasn't explicitly in the technical blueprints, but it has been lingering in my mind throughout this entire exploration.
Lay it on me.
As our PCs evolve from these cold, reactive tools into proactive, autonomous teammates with their own local reasoning, how long until our relationship with the machine fundamentally changes?
Right.
When you are managing concurrent agents, delegating complex tasks to them, relying on their analysis, and perhaps even arguing with them over creative choices in a video edit, how long until we start treating our laptops not just as appliances, but as genuine colleagues?
Wow.
And when that inevitable psychological shift happens and our closest daily collaborator is made of silicon and unified memory, how will that change the way we value the messy, unpredictable spark of our own human intuition?
That is the ultimate question of the AI era.
Yeah.
Because if the machine can flawlessly execute the vision, coordinate the files, and render the output perfectly, the only unique, irreplaceable value left in the entire economic chain is the human spark that generates the original vision in the first place.
The architect remains essential, even if they never swing a hammer again. That tiny sticker on the laptop chassis is changing the world. But the biggest change isn't what's happening inside the computer, it is what's going to happen to the human sitting in front of it. Thank you for joining us on this massive deep dive. Stay curious, keep exploring, and we'll see you next time.